Hello and welcome to Observability with AWS. My name is Rich McDonough. I am a Senior Specialist Solutions Architect with Amazon Web Services. And today we are going to be demystifying observability tools and best practices. On the agenda, we will first be discussing well-architected principles and best practices for how you can use observability tools in your applications. We're then going to move on to some of the details of observability and how it differs from monitoring and alerting. Most of our time will be spent doing a demo of the services and how it can be used to diagnose problems in your environment. Then we're going to open up the floor to questions and discuss next steps. First, some notes around well-architected. The AWS observability tools, they work together with the well-architected framework to help you operate and create workloads according to our best practices. The well-architected framework itself has 5 pillars. There's operational excellence, security, reliability, performance, efficiency, and cost optimization. Using the well-architected framework allows you to leverage the experiences of other builders and the learnings that we have had at Amazon Web Services from working with thousands of other customers. So first, let's set the stage. What is observability? We like to think of observability as a way of inferring the internal state or health of workload based on its external disposition and its outputs. This differs from just monitoring, which is very often more of a red light, green light type of system that tells you if a system is down, but it doesn't help you understand why it's down. Good observability helps you to answer the questions that you didn't know that you needed to ask or didn't know that were important. And very often, these are the why questions. Why is a system behaving in a particular way, as opposed to just knowing that it is not behaving the way that you want it to at a particular point in time. So now let's look at a typical troubleshooting workflow that DevOps and system administrators and developers everywhere will experience. First, an error occurs. A system goes down. A website goes down. Something bad happens. This is usually followed by an alert. So your aforementioned monitoring and alerting system will issue an email or will page somebody. And then this leads to a trouble ticket being created. This first stage of troubleshooting is referred to as the mean time to detection. And customers are generally very good at being informed when something has gone wrong. But then we move into the identification phase of troubleshooting. And this is where things can get very hazy. You might have a site reliability engineer who needs to analyze metrics. And perhaps that leads him to start looking at the logs from a system. But perhaps that individual doesn't have the skill set or the experience or even the access to the actual systems that operate this workload. They may need to engage with developers in a whole other business unit to help them analyze trace data that could be coming from an application. And then they might have to work very, very hard to correlate this data from across all these disparate systems and come to a reasonable understanding of what has gone wrong in their environment. This can be especially challenging if a customer is operating a complex microservices environment, or if they have multiple integration points with third-party software vendors or SaaS vendors. We refer to this time as the MTTI, or mean time to identification. And this collectively is where customers have the greatest pain in dealing with issues that occur in production. The tools that AWS brings in this regard are meant to reduce the mean time to identification, compress how long it takes to figure out what has gone wrong in a complex environment, and then enable you to move on with fixing the environment quickly and getting on about your day. So let's double click on this with a maturity model. At the base of this model are the 3 basic forms of data that are used in observability: logs, metrics, and traces. Now, we could view this as a pyramid, and if we did so, we would see logs, metrics, and traces as forming the foundation of this pyramid. Upon this data, we're able to build analytic capabilities. And this includes common things like forecasts, so predictions for where an application should be performing given a certain time of day or day of the year. Think about a flash sale, or think about when Amazon has Prime Days, for example. There will be predicted behavior that a complex system will exhibit that can be forecast, and that you can have alarms created around to tell you if a system is behaving abnormally at that point in time. But having logs, metrics, and traces, and even analytic capabilities, it doesn't really build a very mature model for gaining observability. As customers grow their capabilities, as their maturity grows, they get to do more with this information, and they get to have true correlation and insights. The classic example of this would be a complex e-commerce application, which has separate systems for fulfillment, user management, shipping, payment processing, etc. And if you need to understand a complex interaction that a customer has had across this vast architecture, you're going to have to correlate it across all of these different domains. As your maturity grows, and as you're able to use greater and greater observability in your day-to-day operations, you'll eventually grow to the point that automatic root cause identification can be brought into your environment, wherein your mean time to identification is brought to a much shorter period of time. And as a result, your business is able to operate much more effectively. So now let's look at the AWS services that form the foundation of observability, the aforementioned logs, metrics, and traces. So first, what are metrics? So these are typically time series data represented as numbers. This will be gauges and counters. They will be things like metrics from a CPU, such as your CPU utilization. It could be a sum of the number of purchases that have taken place over the previous hour. Logs will be generated by one application at a time, and they represent events that have taken place from within that application. Typically, this may include things like stack traces if an error has occurred in an environment. Likewise, it can include diagnostic information that could be useful for developers who are debugging their programs later on after the fact. And finally, there's traces. Traces is where customers very often need to spend more time developing their capabilities. Traces record user interactions across one or more different applications. So referring back to the e-commerce application example, if there is a user who attempts to purchase an item on a site, the action that the user does is singular. They may click the Buy Now button. And when they do so, especially across a complex microservices environment, a whole symphony of actions may take place under the hood, involving fulfillment systems, payment processors, other services that may check the quantity of stock is adequate to fulfill a customer's request. And if you want to track this customer's activity across all of these different systems, traces are going to be necessary to provide this information for the individual who is performing a diagnostic action after the fact. The three services that compose these three pillars of observability are Amazon CloudWatch Logs, Amazon CloudWatch Metrics, and AWS X-Ray Traces. Now, of these, metrics and traces have two features that have to be highlighted. The first is that this data is immutable after it has been ingested into our systems. And this is on purpose. While you can send data after the fact into these systems for analysis, you can't change data after the fact. And this is very, very important for those who need to have non-reputability and truly understand the state of their system at a particular point in time. The second feature is that trace and log data, it can be encrypted using key management service, giving you the ability to bring your own customer managed keys to the environment if this is a level of data protection that you require. The foundational services of CloudWatch logs, CloudWatch metrics, and X-ray traces then enable this entire suite of higher level tools that are built around them. And you see those tools here. Seen here are the AWS Cloud Native Observability tools, all of which are designed to enable cross-application correlated findings that will shine a light into your application's operational health and KPIs. It must be highlighted that observability is not limited to infrastructure or application monitoring, and that a complete solution will do more than just passively yield data for after-the-fact exploration. A well-observed and healthy system will use synthetic monitoring as well to proactively and continuously test an environment's health. This provides both the externalized end-user experience to your monitoring platform, as well as the internal operational health monitoring that you require. Regardless of your application's code, language, purpose, or execution model, the AWS observability tools can provide insights. And users of containers or serverless, compute instances on EC2, or even those customers who operate workloads on premises, they can all benefit from the union of our observability platform. On the right side of the circle, you see the insights services, each of which provides automatic cross-application high-level views of our operational health and request throughput. Service Lens and Metrics Explorer gives you powerful visualizations that can target your entire environment, or alternatively, drill into the metrics and health of a single service as it interacts with the other services that you operate. So who can benefit from cloud native observability? Well, the usual answer that people might leap to is a developer. So here we see a developer, they may be building a new microservice, or they may be doing integration testing with distributed systems, or looking to understand how to best profile a circuit breaker pattern. You would have DevOps who may need to understand an issue as it has arisen in production, or maybe they need to understand network latency over a specific segment, or debug a failed transaction. But business owners also have a compelling need for cloud native observability. They may have a need for real-time KPIs from the workloads that are operating in their environment. This can include things like purchases or interactions with customer service representatives. Now, let's demonstrate what some of these customer experiences actually look like through the AWS console. So with that, we're going to flip over to do a quick demo. For this demo, we're going to be using the AWS One Observability Demo Workshop. This is a freely available workshop that you can view at any time at observability.workshop.aws, and it is available in 4 languages: English, Spanish, Japanese, and Korean. The content we'll be showing today, it is entirely inclusive to this workshop and stands up a pet adoption website. I'm showing this briefly for context, so as we walk through the observability services, you're going to see references to kittens, puppies, and bunnies, and especially things referring to pets and pet adoption. This is the reason why. This mock application that we are going to be walking through composes a complex environment that we find to be very valuable for customers investigating observability services, and what it really takes to understand a distributed microservices architecture in a real-world environment. The environment itself that we're going to be discussing is quite heterogeneous. So we have modules written in Python, C#, Go, Node.js, and we're using a wide variety of AWS services as well, not limited to Aurora, API gateway, step functions, and a number of other features in the container space, such as ECS and EKS. But now to get into the observability components themselves, we're going to start first by showing a dashboard that could be extremely useful for an actual business owner. So I've created one in advance to show some of what is possible using these services without putting a high degree of effort into the building of such a dashboard. So right here, we're showing business KPIs that are targeting an executive within an organization. And even in this view, we're immediately able to link back to the company's internal intranet, or the need to create a trouble ticket for someone within an IT role. They can do so directly from this view. The same business executive can view stats related to customer service representatives, number of support calls per hour, support emails, and they can see alarms related to actual business KPIs, such as failed purchases, or if the transaction time or the number of successful purchases is out of norm for this particular application. Now to go into a little bit of a deeper technical style dashboard, let's actually go ahead and create one so that we can then add some objects to it, gain some more observability into this distributed application that operates this website. I'll just go straight to the dashboards console, create a new dashboard. There we go. And we're immediately asked what data to place into this dashboard. For the time being, I'm going to choose the most simple metrics that I can. I'm going to find metric data. I'm going to scroll down to an EC2 instance, just because observing CPU usage data, it produces a nice spiky graph, which is, it makes for very easy alarm creation. And just like that, we've added CPU for this one EC2 instance directly into a dashboard. Let's go ahead and save that. But now, what if this view doesn't give us enough information? Seeing that we had a spike of up to about 80% CPU at one point, that looks like it might have been a little bit high. And maybe we want to be able to have a little bit better view of what we believe normal is for this specific data point. We can go ahead and edit it directly from here. The first thing we can do, of course, is change the color of the graph. But if we understand well the data that we're actually looking at, then we can annotate these graphs directly from within the dashboard console itself. So let's say a good max value is, let's say 75. All right, there we go. Our max value is now in place. So now we have visibility into the CPU for this one specific EC2 instance. But what if we want to take actions based on if it goes above 75? Well, then we can go ahead and we can create a metric. An alarm directly related to that. So first, we're going to view this data point directly in the metrics console. Clicking the alarm icon will take us to this view where we have the option to use either a standard static value for the threshold for our alarm, or optionally, we could use anomaly detection. Anomaly detection will build a model based on previous data that can tell you what the healthy upper and lower bands for a specific data point are based on standard deviation. You can select which standard deviation value you wish to use. This is a fantastic tool for customers that don't yet know what the upper and lower bounds for an application may be. Maybe they haven't done extensive performance testing, or maybe it's a new application that hasn't been operating out in production for a great length of time. Or maybe there's just more important KPIs than you may be able to keep track of. In these cases, you can use anomaly detection to figure out programmatically, automatically on your behalf, what healthy and good actually do look like. So in this case, I'm actually going to use anomaly detection in the alarm that I am generating. And you'll note the console does give you a forewarning that this gray area displayed is just a preview of the anomaly detection band. And of course, the anomaly detection band, it will change as the model is used over time. Next, once you have an alarm in place, you would want to have an action. Perhaps it's a notification to someone working in a DevOps capacity to inform them that the CPU on this instance has gone out of bands. And the most accessible, the most common way that people get started is using an SNS notification, which can of course be fed directly into somebody's email. Alternatively, you can use SNS as a mechanism to trigger advanced workflows, or to create tickets into trouble management systems, or to even execute lambda functions, which could automatically remediate an issue. You can also have an alarm created that does not have any actions associated with it, which gives you the ability to have a dashboard view of things that are in an error state without having to page an administrator overnight. But there's more that you can do directly from this console as well. If you have an application running in an environment that you know has a problem, that you know requires that its server be rebooted on a periodic basis, as soon as an EC2 instance enters into this error state, you can have the alarm itself automatically reboot the instance. We find this is very, very valuable for customers that operate applications that they have not written, that perhaps they don't have access to the source code for, or that come from an ISV. Applications that have memory leaks are a standard example. And sometimes it may just be faster and easier to simply reboot the instance rather than going through heroic steps to try to bring the application back up, particularly if it's an off-hours time frame when these errors have actually taken place. You can also invoke Systems Manager actions directly. You can create ops items, or you can create incidents using Incident Manager. For the moment, though, I'm going to proceed without any actual actions enabled for this alarm. I'm going to give it a name, say CPU alarm 1. After the review screen, we'll create the alarm, and away we go. So now, with this alarm created, it doesn't do us much good unless we're able to see it. So we're going to add it to our new dashboard. Perfect. Let's just expand this so that we can see it easier. Excellent. Now, there's another view that we can have for alarms, which is also very useful. We can add the alarm status widget, in which case we can select one or more alarms. We can add them directly to the dashboard from this view. Excellent. So now our dashboard has a lot more activity on it than it did when we first started. Now, dashboards themselves, they don't have to be limited to people who use the AWS console, and you can share dashboards with an external audience. And there's two different modes in which this can operate. One is you can share a dashboard using just a username and password. We don't always suggest that customers do so if they have access to the alternative method of sharing a dashboard, which is using a single sign-on provider. You can also share a dashboard publicly if you so desire. Now, if you share a dashboard using a single sign-on provider, it will share all of the dashboards in this AWS account. But the users who access the dashboard do not need to have access to the AWS console. So coming back to the example of a business user, so somebody who's looking at your metrics and KPIs from a sales perspective, or perhaps from a managerial support perspective, they don't have to view dashboards in this console. I can actually show that experience right now. This will pass through a Cognito identity pool and then send the user back to a view of the dashboard completely outside of the console, in which case their view will be extremely similar to this. This is also a very good approach for people who need wallboards or, again, need to share data with other parts of their organization who don't work in a highly technical capacity or have access to the underlying data itself for security reasons. So with that, let's actually move on for a moment and go back to alarms and talk about one of our best practices. So alarm fatigue. It's how we refer to it when a customer receives far too many alarms and they become desensitized to it. An example would be if you have an administrator that has 100 different servers that they operate, or 100 different instances. And if these instances will periodically fill up their disk, they may receive 10, 20, 30 alarms per week or per day even, indicating that the drives on these instances are becoming full, in which case they become rapidly desensitized to these alarms coming in. And that's just a bad situation, because then the important things that people do need to take immediate action on are lost in the noise of the overall alerting system itself. We can create a composite alarm, which is an aggregate of multiple alarms within CloudWatch, and we can set rules around it. So only send an alarm from a composite if conditions are met. So in this example, we would only send this composite alarm if the CPU alarm is going off, and if failed purchases has been triggered, and if a synthetics alarm has been triggered as well. Composite alarms are a very useful tool to help fight alert fatigue. In this case, we'll just create this here. Call it composite 1. And away we go. And likewise, of course, we can add it to our dashboard. Having created this composite alarm, let's move on to talk about logs. CloudWatch Logs has two concepts that customers need to understand. The first is the idea of a log group. Now, a CloudWatch log group itself will have a distinct name per account and region, and a retention setting. The default retention setting is to never expire your logs. We obviously advise our customers to set a retention setting for their logs that makes sense for their purposes. We don't suggest that you have your logs set to never expire unless you have a very specific need to keep this data for an undetermined in advance period of time. You can also encrypt your log data using a KMS key. So this does allow you to keep your data encrypted using your own private key material if you wish. Now, inside of each log group, you're going to have discrete log streams. And the content of these streams is going to vary depending on the application that produces the data. So for example, here we are looking at some of the information related to container insights, a service I'll show in just a moment. This actually has telemetry data that is emitted by containers that exist in your environment. Having a quick look at one of these log streams, then expanding it, we can immediately see that this application emitted its data as JSON, and this is being used by other applications to actually understand from a metric perspective the dimensions of the applications that are running inside of this ECS container. All right, so now let's go through what I believe is a little bit of a more rich example. Visiting logs insights, we see a query engine that we can use to analyze this log data. So for this, I'm going to actually look at the flow log information from this environment that we've created. So this will include all of the flow log data, even traffic that originates from one private IP address and targets another IP address. And this is all organically generated data, and it comes from a traffic generator that operates inside of the workshop itself. And here we see an example where we have a single flow that is initiated from this IP address here, this 11.0, and has targeted another 11.0. The flow is accepted. We see the interface ID and some of the other vital information about this flow. However, if we want to do more interesting analytics around our VPC flow logs, we actually have a number of canned queries that customers can explore on their own as they wish. So here we can apply this query, and right away over the previous 1 hour window, we will be able to see the average minimum and maximum bytes transferred between specific source and destination IP addresses. We can look at IP addresses that are using UDP. There it is right there. So right away we can immediately identify some source IP addresses that perhaps are doing far more DNS queries than others. And here's a particularly useful query. This is statistics around the number of reject packets that are being sent as sorted by the source. So consider the scenario where somebody is doing port scans against your application environment. They could be performing a reconnaissance, perhaps bad actors. These individuals would stand out in a query of this type, and it would allow information security operators, DevSecOps, to perhaps block suspicious IP addresses that are surveilling your environment. And this data is readily available directly from inside of the Logs Insights console. However, it's not very likely that you're going to be diving directly into your logs without trying to understand a bit more of the broader context of the health of your applications. So now I'm going to visit Container Insights. This will give us an excellent high-level view of the health of our containerized applications. Let's go to the container map view, and what we see here is Container Insights has automatically drawn the service dependency map. It's created a graph, essentially, of the containerized applications that operate in this environment. Now, there's a lot of different applications here for us to examine. I'm actually going to filter this down to just my EKS cluster itself. There we go. Zooming in a little bit. So we see at the top the cluster. This mid-tier contains the namespaces. And we see that we have a hotspot here in the pet site service. Average CPU 61%. It seems to be a busy service. Let's click on it and understand a bit more about how healthy it is right now. So we see CPU utilization. It is well used. Memory utilization appears to be healthy. Network transport, of course, is showed. There's no alerts that I've created specific to the service at this time, but we do have a link here directly to the logs from this one application. So at a glance, if we see that there's a hotspot on one of our containers, we're able to immediately identify it visually using the color of the node, and then dive directly into the logs being emitted from it. Logs Insights has automatically populated the query for us, where we're filtering for things that have the kubernetes.pod name value already populated in them. Now, an important note about Logs Insights is it is able to automatically parse JSON data. So as data has been received by CloudWatch Logs, as it is identified as JSON, it's able to index this data for us without having to put any effort into this indexing itself. And everything that relates to Kubernetes hosts, the namespaces, the pod ID, and of course the raw log message itself, all of these things have been pre-populated by Logs Insights, and we can query them at will. It's actually a very long log message that we have in this particular case. This tool, Logs Insights, especially used in combination with Container Insights and with Lambda Insights, allows very easy access to understand the health of your environment at a high level without having to dive through log files that maybe exist on individual EC2 instances. Lambda Insights has a similar view where we're able to see for one or many Lambda functions at a glance vital statistics such as invocations, errors, duration, etc. Specific invocations of a Lambda, and likewise the actual application logs themselves from each of these separate Lambda functions. So far, we've shown 2 out of the 3 pillars, if you will, of a good observability. So we've shown metrics, we've shown logs. Now it's time for us to move on to traces. So while we can get to some trace data from the Lambda Insights console, I'm instead going to go to Service Lens. And instead, we're going to have a broader view of both across Lambda and containerized applications and other services that are neither, or perhaps are third-party web services that you integrate with. I'm going to limit my view to the last hour. And in this graph, we see S3 has been recorded. We can see the latency average for our request to S3. Here is this pet search container. I'll zoom out a little bit here so we can see a little more. There's a DynamoDB table that is used in this application, 145 millisecond average latency. And we have Lambda functions. In this graph view, the nodes represent services, and the edges represent the response time between them. Now, because of the way this application has been created, the response time between each of these should be very, very fast. But there's something that's standing out here that we need to zoom into a little bit. There's a Lambda function that has red around it, and we see that there's a 6% error rate related to executions of this function. So we click on this and get a little bit of a deeper view. Right away, we see there is a 3-second spike in latency. That looks like it would be a timeout. Knowing that we have a service in our environment that appears to be in some trouble, let's view the application traces for it. Here we go. So from the traces console, we can zoom in on any one of the services that we have recorded segment trace data for. We're going to remain in this one service for just a moment. We still see that 6% error rate. We can view some other vital statistics. We could filter for response time or HTTP method. But first, let's actually look at the distribution of responses in terms of response time. Far out of the 99th percentile, we do see a response time of almost 5 seconds, which is extremely long. But let's have a look at some of the actual traces coming from this application, the raw data. So zooming in on this one specific request, we see that there's a new map that's been drawn. This is the interaction between microservices involved in the servicing of this one request from this client, this one snapshot in time. We see that it involved the pet site microservice, there's an SNS call, another ECS container was involved in servicing the request, as well as a call out to Amazon.com. There's a step function that had 722 millisecond average response time. That's pretty long, an API gateway. Let's scroll down and see if we can understand more about what's happening. And right in this view, we can see the segments that are recorded as a part of this application trace. Customers have the option of creating their own sub-segments in code if they wish. So if you wanted to instrument individual calls to specific APIs, or how long it takes to calculate something inside of your own applications, you can optionally do so using the X-Ray SDK. But here we see how long it took to publish messages, send notifications. Multiple microservices will compose a single trace. What we see here is the activity from one user making one request to our entire application. And it's involved calls to many microservices throughout the environment. But let's highlight this pay for adoption call. And then let's go to the bottom and see some of the most important details of this call. So there's the unique segment ID, relates to a parent ID, as you would expect. We have the resources required for the generation of the trace. In this case, this was created by the X-Ray client for Go. There are custom annotations that are used as part of this trace. So if you operate an application that requires you to be able to backtrace activity of a single customer, or maybe if you operate a multi-tenant environment, or if you need to have the ability to have a single transaction ID be traceable throughout 1, 5, 10, or even 50 different microservices, you can create your own custom annotations that will follow your trace as it goes through the entire lifecycle of a customer request. And at the bottom, of course, we see more logs that are related to the servicing of this request. These logs are pulled together from across all of the services that were used to service the request. And that's why we see API gateway, we see lambda executions, more API gateway, an ECS container, and so on. And of course, a backlink over to CloudWatch logs insights, so we can further analyze this data if you so desire. So remember, all of this data that we have in place here, all of it has been drawn from across all of these different vast microservices that exist in our environment. But we can go even deeper than that. By using the X-ray Analytics console, we can even further analyze the vast amounts of trace data that we've been collecting. And we can actually perform more insights around it than you can directly from inside of CloudWatch today. So even just visiting the root of the X-ray Analytics console, we still see the response time distribution. And if we scroll down, we're going to see the list of traces that have been recorded from the environment, discrete user agents, and so on. If we go to traces, let's take any random trace here as an example. Here we go. Similar to the view from within the CloudWatch console, there is a dependency map that has been drawn. This particular trace is a very simple one. This has actually been created by a synthetic probe, Canary, that has pulled the root of the web page that we are operating and is making sure that it is healthy. Or we can go to the Insights view directly, and we can see information that's been gleaned about our environment by the X-ray service itself. And it's identifying that incidents have occurred. So here we see it identified a time frame automatically. I didn't have to put any work into this. There's been a time frame identified when there was a service anomaly. And as identified, that is in a step function, in a state machine. We see another view of the service dependency map, and during this time frame, we see there was a very large number of failures that took place within this specific application. And going even deeper, if we analyze the traces specific to this fault as identified by X-ray Insights, we see a very different response time distribution. And we see the list of traces that compose this specific insight. Now, let's take any one of these and let's dive into this trace and see what it reveals about what took place in the environment during this period of time. There we go. I see a red circle around this one specific step function state machine. If we scroll through the trace itself, we're going to get to the red. Here it is. This is with issues related to reading from a DynamoDB table. And we see the offending resource itself. In this case, this is the ARN for a specific step function. And here we see the exception message that was output. The cause cannot be determined because the lambda did not return an error type. In this particular case, this is a case of a lambda simply timing out. Now, with X-ray, just like with CloudWatch logs, we do support encryption. So if you need to encrypt your data, perhaps even using your own customer managed keys, your own private key material, you can do so using AWS X-ray. All right, fantastic. So now with that Canary created, we actually won't have any data from it to view right away because it doesn't have a history of runs. So what we can do is look at one of these other canaries that I previously created against the same web page, and we can view the results that they had. So here we see an example of canary runs, and this has been obviously a highly successful one. There's 2 failures that took place. If we go to screenshots, we do see the screenshot that was captured at the point in time when this canary actually ran. We have the logs from the execution. But very, very interestingly, we can see how long it took to pull every element from that web page and display it on the virtual browser that captured the actual screenshot itself. So here we'll see the various CSS objects took 19 or 29 milliseconds to actually draw, and we have the request and response headers from each of those as well. So likewise, if you're serving more than just HTML off of a web application, you can examine each of those objects in turn and see which may have taken far longer to have actually come back out of your application than you may have expected. And this does, of course, include objects that are served off of your domain as well. So you can form a very well-informed, very intelligent view of what it has taken to really draw an application out for your end users. So now that we've seen the AWS console experience of what our observability tools can do, let's compare the typical troubleshooting process that we showed before to what it looks like using the AWS Observability suite of tools. So at the top, we see that the mean time to identification has effectively been compressed. And we've managed to look at logs, metrics, and traces and correlate this information all more or less concurrently using the AWS console. Service Lens gives us a very convenient top-level view of all of these data types and lets us not have to context switch between tools on various different platforms stitched together from the personas of other users who may or may not have the runtime experience with the application to perform an effective diagnosis. So what's next? You can visit the One Observability demo workshop yourself today at observability.workshop.aws. The entire environment that we have just shown you, this is available for you to view on your own. It's available in 4 languages: English, Spanish, Korean, and Japanese. You can stand up this entire demo environment along with its complete complex microservices architecture on your own if you wish, or you could, of course, just explore the lab material for yourself and use that to help you learn more about how to use these tools on our platform. Also, please visit the monitoring and observability page on aws.amazon.com to find out more information about monitoring and observability on our platform. I want to thank you very, very much for attending today. Please do reach out with questions. And actually, at this point, I'm going to open up the floor to questions, and we'll be happy to answer any that you have.